Hello everybody, welcome to my presentation. Let's start here with something familiar, a vape pen. Every time someone inhales from this, they're taking in nicotine, a molecule with enormous power chemically, biologically, and socially. The chemistry we're going to explore helps explain why nicotine is so addictive and why that matters. This molecule has contributed to a global public health crisis, especially among the youth. Ethically, that raises questions. Why are flavored vapes marketed towards teenagers? Should companies be allowed to profit off addiction? Economically, the vaping industry makes over $20 billion a year, but the costs to society, mainly healthcare, lost productivity, and addiction treatment, may be even higher. So, understanding the chemistry of nicotine isn't just academic, it's a daily life decision for millions of people, especially young people like us. Let's break it down. Here are the molecules. This one's nicotine, and this is acetylcholine, a natural neurotransmitter in your brain. Their structures are different, but also strikingly similar. Both have nitrogen atoms in a similar position and can interact with the same receptor in the brain, the nicotinic acetylcholine receptor. But here's the twist. Nicotine is more hydrophobic, meaning it crosses into the brain faster and it stays longer at the receptor site. That structural mimicry is the first key to understanding how a molecule from a tobacco plant can hijack your brain's reward system. Let's break this down using data analysis. The column labeled receptor affinity, Ki, or inhibition constant, tells us how strongly a molecule binds to a receptor. It's measured in nanomolar, which is 1/1000th of a mole. Ki is determined using receptor binding assays in a lab, where scientists track how much of a molecule it takes to occupy half of the receptors. Therefore, the lower the Ki, the stronger the binding. Nicotine has a Ki of about 1 nanomolar, very strong, while acetylcholine's is about 1000 nanomolar, which is much weaker. That means nicotine binds up to 1000 times more tightly. But notice the plus or minus values. Nicotine's Ki is 1.0 plus or minus 0.3 nanomolar, and acetylcholine's is 1000 plus or minus 200 nanomolar. This uncertainty could be due to temperature or lab method. It's critical to include because it tells us how precise the data truly is. But even with this margin, the trend is still clear. Nicotine is vastly more potent. And to illustrate the difference in potency between these two chemicals, here is a bar graph, with this bar representing acetylcholine, and this one representing nicotine. Let's look at how this plays out in your brain. This is a synapse, the space between neurons. Normally, acetylcholine travels across the gap, binds to a receptor, triggers a signal, and is broken down in milliseconds. But when nicotine arrives, it binds to the same receptor, but more tightly and for longer. We're back to where we started, but now we understand what's happening. A single chemical, structurally similar to one your body makes naturally, binds more tightly, lasts longer, and rewires your brain's reward system. That's the chemistry. But what should we do with this knowledge? Should we restrict the marketing of vape products to young people? Should we invest more in education and addiction support? Should we be more transparent about how chemistry can be used and abused by corporations for profit? This is where ethics intersects with science. These decisions we make about nicotine and public health don't just affect individuals, they affect communities, economies, and the future of the world. Understanding chemistry helps us make these decisions wisely. I'd like to shout out my friend John McHenry from BHS for helping me come up with the idea and medium for my presentation.
I started laughing. Hello, everybody. Hope you enjoyed the presentation. Thank you. Was that tough?
That was tough.